Hi everyone, welcome to this presentation. Today we are going to continue with another exciting topic about physics. Today we are going to talk about the Earth-Moon system. So we will see first an introduction, then we will see two-planet system as a first example. We will see how to calculate the Earth-Moon trajectory. We will implement a numerical solution to calculate this trajectory. We will see how to implement this solution in WinPython, and finally we will show the results. In this video we will be using some ideas and concepts that we have seen before in previous videos. Physics number 1, how to calculate the Earth's orbit. So for more information please take a look at this video. This is the common Earth-Moon system that we study in secondary school. The Moon is orbiting around the Earth following a circular orbit. Then we have the force that the Earth is exerting on the Moon, which is this force here, F2, with this value using the gravitational law. And then we have the centripetal force on the Moon due to the circular movement, which has this value here. So the Moon is in this orbit because these two forces compensate, so they are going to be equal in magnitude. So from these two equations we can get, for example, the radius of the orbit as a function of the mass of the Earth, and also as a function of the speed of the Moon on its orbit. So if we know these parameters, the gravitational constant, the mass of the Earth, and we know the speed of the Moon, then we can calculate the radius of the orbit of the Moon, which has this value here, approximately 381,600 kilometers. However, if we think a little bit more about this model, we will see that this situation is not possible because the Moon is also exerting a force on the Earth, F1, which this value here also given by the gravitational law. So if there is a force on the Earth, then there is also an acceleration that can be calculated using this expression. So if there is an acceleration on the Earth should be moving in the direction of the force towards the Moon, and eventually it will reach the Moon, and this would be catastrophic. So there must be other explanation to justify that the Earth and the Moon are keeping their relative positions without colliding with each other. Let's study first the case of two twin planets, exactly with the same mass, both of them, so there is no reason why one of them should be orbiting the other. So the possibility that we have to keep these two planets without colliding each other is for them to describe a circular orbit around the middle point here. So with this situation, the forces, the gravitational forces, will be given by this expression here, and the centripetal forces, Fc, will be given also by this expression. So if we equal these two forces, then we have this radius for the orbits. If we know the speed, or if we know the radius, we could calculate the speed with this expression here. So in this situation we can see that all the forces are equal, so the planets can be on this circular trajectory around this middle point B, which is the center of mass, barycenter of our system. We can consider now a more general situation in which we have two planets with different masses, M1, which is bigger here, and M2 here. So the possibility that they have to keep their positions is to rotate around the barycenter of the system. The position of the barycenter, or the center of mass of the system, can be calculated with these expressions here that we know from basic physics, and in the case of two objects we can obtain this expression here. So finally, by using this expression we can calculate the distance of the planet 1 from the barycenter R1 with this expression, which is proportional to the ratio of the masses to the total mass of the system, and also R2 with this other expression here. And from then we can also obtain that these quantities R1 over R2 is equal to M2 over M1, which we can call the mass ratio Rm. So the situation is like this. We have the two planets describing circular orbits around the barycenter, M2 also a circular orbit, always both of them in front of each other, so the forces are going to compensate, and then we can calculate with these expressions that we can see here the gravitational forces and the centripetal forces. So in order to be or to keep their positions, and all the forces have to be equal. So by equaling these expressions here, we can obtain the different speeds and radius, and also we can obtain an important relationship from this equality here. We can obtain this ratio between the speeds, the masses, and the radius. And if we take into account this expression for the linear speed of the planet on its orbit, then we can obtain finally this conclusion that the ratio of the radius R1 over R2 has to be equal to the ratio of the masses M2 over M1, which at the end is the condition of the barycenter. So this explains why they can keep their position by orbiting on a circular trajectory around the center of mass of the system. Let's illustrate the movement of both planets by doing simple animation. So we can see that the movement would be like this. However, the general situation is not so simple, because in general the trajectories that are going to follow the planets can be ellipses, so it can be much more complicated to obtain the final trajectory. We are going to calculate that by using numerical solutions, but the idea is that in general the trajectories are going to be elliptical. These ellipses are situated, so one of their focuses corresponds to the barycenter of the system, and the two planets are always in front of each other, the line joining the two planets going through the barycenter. So the forces, the gravitational forces and the centripetal forces, are going to compensate. So now we are ready to investigate the Earth-Moon system. Let's start by calculating the position of the barycenter. We know the mass of the Earth and the mass of the Moon. So from the equations that we have seen before, we can calculate the distance R1 from the center of the Earth to the barycenter B, and we obtain this value here, 4,670 kilometers, which is lower than the Earth radius, which is around 6,371 kilometers. So we find that the barycenter is below the Earth's surface at a position, as we have seen here, around 4,600 kilometers from the center of the Earth. So the Earth is going to describe an orbit surrounding this barycenter, and also the Moon is rotating around not the center of the Earth, but around the barycenter of the system. For calculating the barycenter, we have used here this average value of the distance between the moon and the Earth, just for having an idea about the position of the barycenter. Also, the positions R1 and R2 of the Earth and the Moon from the barycenter can be calculated by using this expression here as a function of the mass ratio, Rm. So the situation of the Earth-Moon system is like shown here. The orbits are elliptical, as can be seen. We have exaggerated the dimensions of the Earth orbit by locating outside of the Earth and the barycenter for better clarity. So at a given instant, the position of the Moon could be like this. These are the coordinates of the Moon. We are taking the origin of our Cartesian system on the barycenter. Here, the Earth will be a position like this one with these coordinates, and on the line that joins the Moon and the Earth going through the barycenter. So we have the expressions for the forces, gravitational forces here, F2 and F1. And also another expression with the distance between the Earth and the Moon. So we have this expression here for this value R12. So in order to determine the trajectories of the Moon and the Earth, we need to calculate the accelerations. The process is exactly the same as we have seen in this previous video, physics number 1, how to calculate the Earth's orbit. So, for example, for the case of the Moon, we have the gravitational force that can be decomposed into components here, F2y and F2x, and the magnitudes of these components can be obtained here by inspections of these triangles here in the diagram, and from this we can obtain the magnitude of F2x and F2y, which are going to be equal to the mass of the Moon times the acceleration in the x direction and also times the acceleration in the y direction for the case of the force F2y. So from this we can obtain the components of the acceleration of the Moon here in the x direction and in the y direction. We have to note here that R12 is the distance between the Earth and the Moon, and R2 is the distance between the Moon and the barycenter. Similarly, for the case of the Earth, we obtain these equivalent equations, and the three parameters related to the distances are R12, which can be calculated as a function of the coordinates using this expression here, R1 and R2. And then using these equations we can start our iterative process by starting at a given point on the trajectory, so we can obtain the increment that we are going to have in the velocities in the x direction and in the y direction by using these expressions here, the new value of the velocities by adding this increment to the previous value. And then using these expressions here we can calculate the new position of the Moon in this case by adding the average velocity times the time interval to the previous value of the coordinate. We have seen in detail this in this previous video here, physics number 1, so for more information please take a look at this video, and we can follow exactly the same process to calculate the new components of the Earth velocity and also the new values of the Earth coordinates. We are going to take as the starting point for calculating the different positions the position of the Moon at the apogee, which is the farthest position of the Moon from the Earth. And we are selecting this position because it is very easy to find the information in the literature. Basically, we have as input the distance from the Earth to the Moon, RA, which can be found from the literature, and also the speed of the moon in this position is another input, and it can also be easily found from the literature because this is the lowest value of the speed of the moon. With this information we can calculate the coordinates of the moon and the earth using the expressions that we have seen before here and here. For these two distances, the y coordinates are going to be equal to 0, of course, and then we only have to find the speed of the earth, which is not easy to find from the literature, but we know that the speeds of the earth and the moon are related by this expression here that we have seen before. So this is valid also for this starting position. So by using this relationship between them, then we can calculate the value of the initial speed of the earth. So with this we have everything, and then we can implement our numerical algorithm to obtain the trajectories. Here we have the implementation in WinPython. We start with the input data, the gravitational constant, the masses of the earth and the moon, the mass ratio, the distance at the apogee, and then we calculate with these expressions the initial positions and velocities of the earth and the moon, as we have seen in previous slide. Then we have selected this interval here in seconds for the delta t interval. We are going to calculate one full rotation of the moon. So the period of the moon is 27.3 days approximately times 24 hours times 3600 seconds. With this we determine the number of points that we are going to calculate, and we define the different arrays that we need to evaluate the different variables. All of them are well known from the slides before. R here is the distance between the Earth and the moon. So here continues the script. We have here the increment in the velocities for the Earth in the x direction and in the y direction. We have defined here two functions for doing this, and also for the case of the moon. Then we have the initial point with all the values. We calculate here the first iteration that we have seen in the previous videos in this playlist, and then here we have the expressions for the general iteration loop, in which we are using for more accuracy the average value of the velocities in the current iteration and in the previous iteration. So now we can run the script and see the results. Here we have our script as we have seen in the previous slide. This is the same information, and now here we have this part with the different plottings that we are going to see now. So this is just to plot the arrays. If you are not sure about how to do this, please, there is a playlist about WinPython, so take a look at these videos related with WinPython. So now we can run our script and see the results. Here is the number of points that we are calculating. It's around 131,000 points. And then we can go to plots and see the different results. Let's start from the beginning. Here we have the orbit corresponding to the Earth in blue. So remember that this is the trajectory that is following the center of the Earth. So we can see the dimensions here. This is a little bit more than 4,000 kilometers. Here is something like 4,500 kilometers. This point is the origin of our system, which is the very center of the Earth-Moon system. Then we can see the trajectory of the moon. In this case, the distances are much bigger. Here is something like 400,000 kilometers. Here is a little bit lower, 300 maybe and 80,000 kilometers. We could evaluate this in more detail by printing the different points. Here we have both the orbit of the moon in red and the orbit of the Earth in blue here. So we can see that the dimensions are very much different. So here the orbit of the Earth appears as merely as a point compared with the moon trajectory. So in order to see this better, we have magnified here the trajectory of the Earth by multiplying the dimensions by 20 times, so we can see the both trajectories, both orbits a little bit better. Here we have the distance between the moon and the Earth, so we can see how the distance is changing. The maximum distance is something like 450,000 kilometers here, and the lowest value is something like 370,000 kilometers. Then we have here the Earth's speed in meters per second. So here we have this minimum value around 11.8 meters per second up to something like 13 meters per second. So this is in the range of 40 kilometers per hour. So it is not a very high speed. And finally, we have here the speed of the moon. So the lowest value, which is here, is something like 960 meters per second up to something like 1050 meters per second. So in principle, everything is okay in our calculations. Maybe you can find some difference between these calculations and the literature. Of course, in order to have more accurate results, we need to consider also the force due to the sun, which is also acting on the Earth and the Moon, and even due to other big planets on the Earth and Moon system. So the conclusion after these two videos is that the Earth is not describing a circular orbit around the Sun, not even an elliptical orbit. What is describing the elliptical orbit around the Sun is the center of mass of the Earth-Moon system. And both the Moon and the Earth are rotating around this center of mass, completing around every 27 days approximately. So at the end, both the Earth and the Moon are describing an helical trajectory around the Sun as shown here, even though the displacement from the elliptical trajectory is very small. In both cases, in the case of the Earth, is only around 4,000 kilometers. In the case of the Moon is around 400,000 kilometers, but in any case very small compared with the distance from the Sun, which is around 150 million kilometers. Well, this is all today in this presentation. I hope that you have enjoyed this video. Please let me know if you have any comment or question. Thanks for watching, and I hope to see you in the next video. Goodbye now.